Just want to check if it works. Yeah, perfectly. Yeah. So I'm going to present a recent work that was published in Article Transactions on Networking. So time-sensitive networks provide performance guarantees over delay and jitter bounds, and some applications require in-order packet delivery and the zero congestion loss. And for recover from transmission loss, they typically have redundancy mechanisms. We have seen interesting discussions about computation of delay bounds. But with the emergence of application with low jitter requirement like industrial Internet of Things or factory automation, there is the need for these applications to provide low jitter. What we mean by jitter is the definition in RC 3393, which is a difference between the worst case and the best case delay. So here we would like to talk about dampers as a jitter reduction mechanism. What damper is actually doing is it equalizes delay by for the packet to be equal to the delay bound of the upstream system. So let's consider a simple example where we have a system with a known delay bound, and then the packet experiences some delay within the system, and then the earliness of this packet with respect to the delay bound, which is actually the difference between the two, is computed and is added to the packet header, the field that we refer as damper header. And then what a damper does is it actually delays the packet as much as the value written in the header, in the damper header. So we could simply see that the packet experiences a delay d here and delta minus t. So actually it experienced in total as much as the delay bound of the upstream system. The original proposal of damper was with work of Verma and Sked Plus of Cruz and RCSP of Zhang. But recently with the with Huawei and the patents that they have with RGCQ and FOPLEC, and also the proposal of a combination of jitter mechanisms with ATS, the analysis becomes more interesting. And that's why we would like to recap that. So a damper in an ideal case, when a packet arrives, so what it does is actually it takes the arrival time and it adds the damper header to it, and it computes some eligibility time for the packet that the packet is then released. So this would be the ideal case. However, because of the implementation inexactness and exact timing and the errors, mathematical arithmetic error, then the implementation of an ideal damper is not actually possible. That's why dampers are often coming with some tolerance. This is what we refer as damper with tolerance, with a lower and upper tolerance. And actually what it does is it releases the packet after the computation of this theoretical eligibility time, and it adds some tolerance. So the actual release time from a damper is something between these two bounds. This is, in fact, this captures all the RCSP and RGCQ implementations are within this family of dampers. But these dampers is simply because they have tolerance, they do not preclude any packet, in-order packet delivery. So that's why some implementations impose this FIFO constraint to the dampers, like the FOPLEC by Huawei or Sked Plus of Cruz. The dampers that we call them resequencing damper, they also have some tolerance. So we model them with these equations, which is actually it computes some tentative eligibility time, which is similar to the damper with tolerance, but it actually imposes some FIFO constraint. Yet another category of dampers, what they do, they implement dampers as a FIFO queue, which is actually the example would be the jitter control asynchronous traffic shaping, where what they do is they only examine the packet at the head of line. And so it computes some theoretical eligibility time based on the arrival and adding the damper header. And as soon as it reaches this value with some error, it releases the packet. And then here is the time that it only examines the second packet as it becomes head of line. So it does the same thing here for the second packet and here, and it continues like that. We refer to, so a head of line damper is actually the family of the dampers that also include the jitter control ATS. It has some tolerance on processing time. So any system that follows this equation, as you can see here, the FIFO constraint here, is a head-of-line damper, including the jitter control ATS. So here there are two parameters. There is the deltas here as a tolerance, which they capture the arithmetic rounding and time in acquisition. And also there is a processing time because we process the packet one by one. So we could make sense of it more when we have a burst of packet just becoming eligible, and then they have to be processed one by one. That's why the processing time comes into play. So what we have seen so far is a taxonomy of dampers, where actually with these three categories that we mentioned, all of the existing implementations are included. So we take this modeling of the dampers that we would like to do the analysis for. To perform this analysis for a flow, what we need to do is to understand the systems and how to abstract them to make it as general as possible. So for the systems that we would like to remove the jitter from, that what we refer as jitter compensated system or JCS, there are any system like the output queuing system of a router switch is the one that we probably would like to remove the jitter from. So these are all the examples of JCS. So what a JCS must be able to do is to timestamp the packet arrival, and also being able to compute a damper header because it needs to be carried over the header of the packet. Another category of these systems are the bounded delay systems. They refer to all systems that we cannot remove the jitter from, or we simply do not want to. For example, for propagation delay, it is 0 almost, so we can count it as a BDS, or the high-speed backbone network. We may not be able to necessarily timestamp the packets. So damper header update unit, how does it work? So in fact, when a packet arrives, a timestamp arrival, and then when we want to transmit the packet, we timestamp again. And then we take the difference and we reduce it from the delay bound of this system. But since the packet is out of control when we start a transmission, we may want to also infer the transmission time, which is simple to do because we only need to have the packet length and then we divide it over the line rate. But this may not necessarily be the actual transmission time. That's why it may come with some error. And also, like acquisition of the time to timestamp, it may also come with some error. That's what we say as the error is in computation of damper header. And we assume that it is bounded by some value. So let's see how it looks like in some practical example. Assume there's a local area time-sensitive network, let's say TSN, and then we would like to implement damper at any system to remove all the possible source of jitter. For example, the damper here, it removes the jitter from the upstream switching fabric and also the queuing of the source. Or another example is a large-scale deterministic network where we have a backbone here, which we don't want to remove the jitter from, and it's counted as a BDS. And the access network is actually implementing a damper, so it's aware of damper mechanisms and timestamping. So that's why we can remove the jitter that is within this access network. The source and destination are unaware of any jitter reduction mechanism, so we just account them as BDSs. So the analysis of such a system is not really complicated because the delay bound would be simply the addition of the delays of JCSs and BDSs and perhaps the tolerance of the dampers. And the jitter bound is simply the jitter of the BDSs because with dampers, we simply remove the ones with within the JCSs. However, in practice, the clocks are not ideal. So the local system of clock may be different from the perfect clock, which is International Atomic Time, where we refer to as TAI. And this makes the analysis a bit complicated. It is not as trivial. We have seen that the effect of non-ideal clock with regulators, that with the work of Ludovic, that may cause some subtleties and issues. So we would like to follow that with dampers and see how it works really with them. So we use the bounds that they computed in their paper with the work of Ludovic, that the error from the perfect timing is bounded by these values. So there are three terms here that I need to explain. So this is the clock stability bound rho, which is some value in the order 1001 in TSN. Or there is this term eta here, which is 2 nanosecond in TSN. And the term omega here is for clock synchronization error bound. And for example, in the case of a TSN with PTP, it is 1 microsecond. And if the network is simply not synchronized, it would be infinity. So let's see how this affects in a simple example when we want to compute an end-to-end delay bound. So we have one JCS here and simply one damper here. We would like to compute an end-to-end delay from here to here. So what would be the steps? So what we do to compute a delay bound, we just decompose this delay to the part that is related to the JCS and one related to the damper. And they're both like in the perfect timing, right? But we have some information for the local delay bound, a delay of the packets within each two. So what we do is we simply add and subtract the local delays with the local clock of the two systems. And what we obtain from this equation is this one. So there is a term that is related to the local delay within the JCS and the damper. And there is a term that captures the measurement with non-ideal clock. So let's see how we bound these two. So it is simple. So here we have a delay bound, a delay for the JCS with local time, and then there is the delay for the damper. We know that the delay of damper is simply the damper header plus some tolerance. And the damper header is nothing more than the earliness, which is the difference between the actual delay within the JCS subtracted from the delay bound. So if we combine them together, we can find the bound for this. For the non-ideal clock measurement, we use the bound that we just presented in the previous slide. We use the upper bound, for example, in this case. We do the permutation of the minimum function, and then we obtain a delay bound, a bound for the variable omega here. And we can do similarly the same thing for lower bound of this by using the other part of the bound, and we obtain a lower bound for the effect of non-ideal clock. And finally, we can obtain lower and upper bound for this that accounts for the non-ideal clock. And in fact, the term size or for the non-ideal clocks, and this epsilon is the for error of damper header computation. And the jitter is simple because we remove the jitter from the JCS, but there is a tolerance of the damper and the non-ideal clock terms. Observe here that we have the term delta, which is a delay bound of JCS that is present in this bound for error of measurement with non-ideal clock. So in a general case, when we have multiple JCSs and multiple BDSs in the system, we follow the same thing with more complicated computation. And we see that the jitter has been removed from the jitter of the JCS has been removed. And this is only due to the jitter of the BDSs. And we see the tolerance of damper here. So the K is the number of the JCSs that we do actually the time stamping for. The epsilon term here is capturing the effect of non-ideal clock. And we see here that the delta is the delay bound of the JCS. So there's a sum of the delay bounds. So in fact, whenever this delay bound is higher, we see this effect of non-ideal clock more. We see in some examples. So this is the local area time sensitive network where the network is not synchronized and everyone is implementing RCSP as an implementation of damper with tolerance. So the damper is responsible to remove the jitter of the upstream queue and the switching fabric. So what we observe is that we could compute an end-to-end delay bound in 1.8 millisecond, and a jitter bound, which is in the order of microsecond, 8.8. The basic jitter bound is easily computed with the damper tolerance. So if we account for only the tolerance of the damper, we see that the jitter is around 7. However, accounting for the errors in non-ideal clocks, it adds 26% to the jitter that was computed without considering it. So it shows some significant effect. If we simply ignore this non-ideal clocks, we may not really capture the amount of jitter. In the case of large-scale deterministic network, when we do not want to remove the jitter of a backbone, so actually the access network here is implementing RCSP instance of damper with tolerance, and they remove the jitter of the access network. So here the delay bound is way more, and the jitter bound is in the order of milliseconds. So and it's mainly dominated by the jitter of the BDSS, which is mainly like the backbone network. And the non-ideal clock does not really affect this jitter bound. So we can also do something more interesting to remove the jitter of the backbone network. So the idea would be that we need to be able to timestamp the packet just before the packet enters the backbone network. And then just in the next provider edge router, we do the computation of damper header. So here, since the clocks are not perfect and they run independent of each other, we need these provider edge routers to be synchronized. So what we could see is that the jitter bound has drastically decreased. You see, it's now in the order of microsecond, and we see that so that the tolerance of a damper captures a small portion of this jitter bound, and it is mainly because of the non-ideal clocks. And it's like, in fact, accounts for 141% of the jitter. And it comes from the fact that the delay bound that we computed is quite large, and that's the fact that we saw in the capturing of the error in measurement of the local clock with the perfect clock. So we would like to give an example of reordering that simply occurs due to non-ideal clock. So the RCSP is an implementation of damper with tolerance. We said that simply due to the tolerance, packet reordering may occur. But RCSP is implemented in a way that the tolerance of the damper does not cause reordering. So it actually, in practice, should not be able to cause reordering. But we see that here, simply due to non-ideal clock, this may happen. So assume that two packets are coming back to back, and they're transmitted. The interspacing between the two packets is simply the transmission time of the second packet. And so the damper headers are computed respectively just by reducing the transmission time of each packet. For the second, since it's waiting for the first packet to be transmitted, we also have the term here. And then if the damper at the end computes the theoretical eligibility time simply by getting the arrival time plus the damper header, we see that the interspacing at the theoretical eligibility time of this damper, it has one part, just is simply due to the error of inferring the transmission time. And there is a part that is the transmission time of the second packet seen from different clocks. So if it happens that the clock of H1, which is the damper, is faster than one from the JCS, it simply says that the transmission time is smaller as seen from the damper than is actually from the clock of the JCS. And it caused simply a reordering because the theoretical eligibility time of the second packet becomes smaller than the first packet. We have seen the analysis for dampers with tolerance. And now we would like to repeat the analysis for dampers with FIFO constraint. So the main issue here is that dampers with FIFO constraint, because they have this constraint on FIFO, even some packets may already have their already being eligible, but they're not sent because it simply wants to preserve this FIFO constraint. So they may further delay the packets. So now we would like to capture this effect in the next slides. We have seen that the analysis or the result is a bit different when elements are FIFO or not FIFO in a network. So first we focus on the elements when the elements are all FIFO. So the rest of the network is FIFO. Focusing on the resequencing dampers, we have shown that a resequencing damper is actually a damper with tolerance that is followed by a resequencing buffer that corrects the order of the packet with respect to the entrance of the damper. We have shown in another paper of ours that resequencing buffer is for free in terms of delay bound. So actually what it does is, if the damper is lossless, then adding a resequencing buffer to correct the reordering happens here, it does not increase the worst case delay and jitter. So simply what we could see here is that if we model the resequencing damper with tolerance and resequencing buffer, it actually is the same delay and jitter bound as the one with damper with tolerance. So the FIFO constraint does not really affect the delay and jitter bound. In another case, when we have a head-of-line damper, we also have another theorem that says that a head-of-line damper is actually a resequencing damper, logically, if you see that follows by a single server queue. So it is simple to see that if the processing time can be assumed to be 0, it is simply the same as resequencing damper. and all the thing that we said in the previous slide is valid for it, and it provides the same delay bound as resequencing damper and as well damper with tolerance. But in case if the processing time is non-zero, things are a bit different, because then we have to account for the delay and jitter of a single server queue. So this is what we capture. So we capture the delay bound of single server queue, as you could see here. And the jitter is simply this delay bound minus the minimum processing time. However, what happens if we have a non-FIFO network? So what we see is that with non-FIFO network, a resequencing damper is not able to remove the jitter of the network. And with head-of-line damper, is the processing time can be assumed to be 0. It is the same, so it cannot remove the jitter. So it does not provide the goal that it has. And even in the case when the processing time is non-zero, it even increases the jitter. So let's make sense of it by an example. Assume that we have this non-FIFO part in the network, and so it has a known jitter for this part, and assume that the first packet experiences the worst case delay and the second experiences the best case delay. So there is a reordering that happens just at the exit of this non-FIFO network. And then the rest is FIFO. It enters the damper. So what the damper sees is that the second packet is before the first packet. So what it does is, even though packet 1 already had experienced the delay that was supposed to, it has to wait until a second packet becomes eligible, and then it sends it. So that's why, like, we first deliver the second packet and then the first packet. So we see that the delay of the first packet is increased, and so the jitter, as much as we see the jitter of the non-FIFO part. There is also another thing. So the order of the packet here is like that. We have the first packet and the second packet. There is a wrong order here after non-FIFO part. And then we see that the damper was supposed to preserve the order, but it preserved the wrong order of the packet. So it even not helping here. So it delays the packet, but even with the wrong order of the So what we have seen so far is that when all network elements are FIFO, dampers with FIFO constraint, they can reduce the jitter and also provide in-order packet delivery. But when there is a non-FIFO element in the flow path, the dampers are not able to remove the jitter, and they preserve a wrong order of the packet. So what would be another alternative is that, like, simply think in a way that maybe we can just simply use damper with tolerance and then put a resequencing buffer after to correct the order of the packet when we are in the case when there is a non-FIFO element within the flow path. So let's see an illustration of what we have just discussed in terms of theory. We would like to see them in the numerical evaluation. This is an Orion network with 40 flows, and each flow sends 10 packets, and the flows traverse from 2 to 9 hops. So the first curve, so we are implementing, so we are examining 3 implementation of dampers. The first one is RCSP, damper with tolerance, a resequencing damper, FOPLEC, and then there is a head-of-line damper with these parameters. So the first figure is that, like, how actually dampers remove the jitter. So if there is no damper, we see that the jitter increases. Well, there is a very high jitter, but with dampers, it is quasi-removed, right? It's like around 0, and it's the difference between the parameters of each damper. The second curve is showing the impact of non-ideal clock with RCSP, that we see that this 11% of the jitter is by non-ideal clocks, and we could not be able to capture it if we haven't done this analysis. And the third is showing the case when there is a non-FIFO element. So non-FIFO element could be a switching fabric that may cause packet reordering. And we see that with resequencing damper, the jitter is not actually removed. And with head-of-line damper, it is way worse, so it increased the jitter. So what we have shown in this presentation is a taxonomy of dampers. We could see that we could categorize all the existing implementation of the dampers into 3 main families of damper with tolerance, resequencing damper, and head-of-line dampers. We present a theory to capture delay and jitter bounds for these dampers. We capture the impact of non-ideal clocks and error in the computation of damper header. We saw with dampers with FIFO constraint and all network elements are FIFO, they perfectly reduce the jitter and provide in-order packet delivery. Otherwise, they fail to perform their goal to remove the jitter. And they also preserve the wrong order of the packet. We show scenarios that packet reordering can occur with one implementation of damper with tolerance simply due to clock non-ideality and computation of damper header. And we saw an illustration of different implementation of dampers within the industrial case study with Orion network. So I have the references, and I think that the slides are already online. So in case if you want, and I will take question now. Thank you.
Yeah, so we
22 minutes.
22 minutes and time for questions. So please feel free to ask your questions or think about your questions while I have an initial one. I was wondering, is it possible that the transmission of a packet by the damper blocks the transmission of another packet, that you have like two packets which kind of should be output at the same time or at overlapping times?
Yeah, I understand. So for example, with the dampers with the, true. So if we have multiple packets that are actually eligible, so it's the question, if they're eligible at the quasi the same timing, are they blocking each other? So this is the question. And so with dampers with tolerance, so for example, in implementation that is existing, so the implementation is in a way that they are like bucketized. So all the packets that are quasi having the same, they go, so this is that we have the tolerance of the damper, for example, in the order of 1 microsecond, right? So that's why like all the packets that are quasi the same eligibility time, they go to in one bucket. And as soon as it reaches, it starts releasing them. So what it does is actually, for example, with RGCQ is an implementation, they combine the queuing system with the damper as one unit. And then as soon as this block, this bin, this bucketized thing is eligible, it just simply make it visible for the queuing system. So they just simply go to the queuing system and they're being served. So it's not like dampers are not the output queuing that the transmission would cause the delay and blocking of the next ones. They actually go to the next queuing system.
Maybe quick follow-up.
Yeah.
The transmission time of a packet compared to the error in clock synchronization, how do they relate? Are these like very short packets? What's the transmission time?
I have not got it. So you,
the serialization delay of one packet in your network.
Yeah.
What time is it? Is it in microseconds?
It depends on the packet size, right? So it depends on the packet size and the line rate, right? So it's the this transmission time is in fact the size of the packet over the line rate, right? So the question is how this non-ideal clock affected.
I was just asking, like, for a number, is the clock synchronization bigger or worse than the transmission time of a packet?
Okay, if the okay, I see. Yeah, I will. So is it like, so it's a comparison between the errors that caused by clock non-ideality and the transmission time? How?
What the effects are. So.
Simply transmission time. I have to see, but it is very variable.
It's comparing apples and oranges.
Yeah, it's.
It is comparing apples and oranges, but to get a grip on this, the clock drift bigger issue, then it may be helpful, but let's take it offline.
Yeah. Well, we can discuss it offline definitely.
The clock drift
is
speaking 10 to the -4 of what you're measuring. That's it. So if you measure 1 millisecond, the accuracy you have on this millisecond is 10 to the -4 milliseconds, so 100 nanoseconds.
Yeah.
So you could.
The clock drift means.
So if you see the bound here, for example, it's like the delta is a delay bound for the previous JCS, which could include just the transmission time, right?
Yeah.
So it's the transmission time would be here, right? And then we have the rho minus 1. Rho is like 1.0001. So the minus would be 10 to the power of -4, right? So if you have a simple transmission time here, what would be is like 10 to the power of -4 multiplied transmission time. If we simply have the transmission time of a packet and not the queuing delay and anything else. If that was clear.
Yeah, thanks for.
Okay.
Thank you for this very interesting talk. Do you have any insight in the overhead created by performing damping? I mean, at 1 gigabits per second, it's negligible, I assume, but if you would speed it up to kind of more current speed, it may not be. There's a lot of work going on. You know, you have to add header, you have to timestamp, subtract.
Well, yes, sorry. So the question is, in high-speed network, when the line speed is very high, because of the complication of releasing the packet and damper header computation, would it be possible to have dampers in this scale, in this speed? So there are two parts. There's a part for computation of header, and there is a part that is like implementation of damper. So two different things. So for the computation of damper header, it's a good question. Like, are we able to do the time stamping when the speed of the input packet is very high? To be honest, this has not been studied, but there might be some issues. It depends on the implementation. That's true. There might be some issues.
I mean, it's an implementation issue.
Yeah, but yeah, we're talking about like very high speed and the time stamping computation.
Kind of what the example that you had was a 1 gigabit per second network. So that's what people are currently working with. They're not looking at something, you know, much faster right now.
True.
So you may
True,
have
but
at extremely high speed. If you have a backbone at terabits per second,
I mean,
the end-to-end jitter that you will have will be below a millisecond. So probably there you don't want to remove the jitter when you are at astronomical.
So we just have to wait until technology
No, but you will always
catches up, and then the word becomes obsolete.
No, but this PC is not connected directly to a backbone, so you remove jitter typically in access network where you have a lot of variability and where it's affordable, and then you go through the backbone quasi-transparently. And we don't need deterministic services across the backbone, probably.
I don't want to kind of nitpick, but I just would be interested in that overhead and how it relates to the when it becomes, at which rate it would become relevant, just to get some bearing. You know, at current, you know, if you're using current speeds.
Well, we're doing an implementation at 10 gigabit per second in
FPGA.
FPGA.
Yeah.
And that's not, it's still negligible at those speeds.
Yeah, well, the overhead is time stamping. You need to know, you need to measure a time when the packet joins, and then you add an additional header. That's the overhead. At 10 gigabit per second, programmable logic.
But
Yeah. But 30 per second.
now you also have to repeat the answer. Yeah, we are slightly over time, but
Or it's still very good session time, right?
questions right now. So there is a coffee break. You can take your further questions.